Hello and welcome. Today, we're embarking on a rather unusual intellectual adventure. We're going to take the ideas of Jacques Derrida, the father of deconstruction, and apply them to mathematics. Yes, you heard that right. We're going to deconstruct the equation. Now, deconstruction is a complex philosophical approach, but at its core, it's about questioning the stability of meaning and the inherent contradictions within systems of thought. Derrida focused primarily on language, arguing that meaning is never fully present, never completely fixed. It's always differed, and dependent on a network of relationships. But what does this have to do with mathematics, a field that seems to be all about precision, certainty, and absolute truth? Well, that's precisely what we're going to explore. Let's take this seemingly unassailable equation. 2 plus 2 equals 4. It seems self-evident, right? But Derrida might ask, what are the underlying assumptions that make this equation possible? What is the system of language that gives these symbols meaning? After all, 2 plus equals and 4 are symbols, signs that represent concepts. They're not the concepts themselves. They're part of a system of differences where each symbol gets its meaning from its relationship to other symbols. The meaning of 2 is defined in part by its not being 1 or 3 or any other number. Derrida might also point out the logocentrism inherent in mathematics. Logocentrism is the belief in a central, ultimate truth or meaning that grounds a system of thought. In mathematics, this often manifests as a belief in the self-evidence of axioms and the absolute validity of logical deductions. But what if we deconstruct these axioms? What if we question the very foundations upon which mathematical systems are built? We've already seen examples of this in previous videos, like the discovery of non-Euclidean geometries, which challenged the self-evidence of Euclid's parallel postulate. Derrida's approach encourages us to look for the aporias, the internal contradictions and blind spots, within any system of thought, including mathematics. For example, the concept of infinity, as we've discussed before, is full of paradoxes and challenges to traditional logic. Even the concept of equality itself, represented by the equals sign, can be deconstructed. What does it mean for two things to be equal? Are they identical, equivalent, interchangeable? The seemingly simple equals sign hides a complex web of philosophical assumptions. So, a Derridean approach to mathematics wouldn't necessarily try to disprove mathematical theorems. Instead, it would focus on unraveling the underlying assumptions, the linguistic structures, and the hidden contradictions that make mathematics possible. It would treat mathematical equations as texts to be read, interpreted, and deconstructed. This might seem like a purely abstract philosophical exercise, but it has real implications for how we understand the nature of mathematical knowledge. It challenges the notion of mathematics as a purely objective, ahistorical, and value-free discipline. It reminds us that even the most rigorous logical systems are built on foundations that are ultimately human constructs. What do you think? Can we meaningfully apply deconstruction to mathematics? Does this approach enhance our understanding of the field, or does it undermine its foundations? Share your thoughts in the comments. And if you enjoyed this rather unconventional exploration of math, be sure to like and subscribe. Thanks for watching.